Hello. So we have reached a milestone today. We are now on the last video lesson of the year. So that's pretty exciting. I'm sure you'll be happy to take a break from watching these videos. So what we're doing today is we're going back to a set of notes that we skipped over at the beginning of the part 2 of solutions. So if you're working out of the booklet, you'll just have to flip back to closer to the beginning of the booklet and you'll find this set of notes. If not, I've attached them in the post for today. So this is just talking, generally in chemistry, we measure concentration in moles per liter. But there's a variety of other ways to measure concentration. And we go over this because a lot of these other ways of measuring concentration, you'll run across them in your everyday life. So you'll notice on, certain household products and things like that, that you'll find some of these other concentrations. So let's take a look at them. Okay, so the first one that we're going to look at is just a simple mass over volume concentration. So this, very, very similar idea to moles per liter, but instead of moles per liter, it would be grams per liter. So this would be more common in like daily life, as the average person has a better understanding of what a gram is versus what a mole is. You guys are no longer just average citizens. You now know what moles are, so you're much more informed. So this says that it measures the amount of solute in grams dissolved per liter of solution. Okay, so how many grams of the whatever the solute is, so let's say it's sodium chloride, would you dissolve in every liter of solution? So for example, 0.5 grams of sodium chloride is dissolved in 100 milliliters of water. Okay, so first, because this is grams per liter, we would convert milliliters to liters first. Okay, so we would go I know you can do this in your head at this point because we've done so many of them, but this is how you'd write it out. There's 1,000 milliliters in a liter. So if you divide by 1,000, you get you can switch it over from milliliters to liters. And then to do the concentration, instead of C equals N over V, we would do M over V, M for mass. So it's just whatever the mass is in grams divided by the volume in liters. Okay, and that tells us that there's 5 grams per liter of solution. Okay, so 5 grams for every liter is what your concentration would be of this particular solution. Okay, so that one's pretty easy to understand. Just another way of looking at it. This one you sometimes might come across. This is percent weight by volume. Okay, so that's definitely a little different than what we just looked at. So the formula is the percent weight divided by volume. You take your mass of solute divided by 100 milliliters of solution times 100. Okay, so you're basically looking at what's the percentage of the solute in the entire solution, and what is its percentage by mass, okay, or weight in this case. So let's do that same situation that we did prior in the last one. We still have our 0.5 grams of sodium chloride in 100 milliliters of water. So we want to know what percentage of the solution by mass is made of sodium chloride. Okay, so we're going to take our 0.5 grams of solute and we're going to divide by 100 milliliters, okay? And then we're going to multiply by 100 to get that as a percentage. So you can just see we're just making this is the how many grams of solute in the 100 milliliters of water. The multiply by 100 is to get it as a percentage. So this is a point. If you do this and multiply by 100, you get a 0.5% weight. Oops. Weight by volume. Okay, so in that solution, just 0.5% of it is the actual solute. The rest is water. So this is a very similar idea, except now we're going percent volume by volume. Okay, so you would use the percent weight by volume if your solute was a solid. So in this case, sodium chloride is a solid, right? It's crystals. You would take like a scoop of it and add it to the water and stir it up. So it makes more sense to do weight because you could weigh out the solid on a scale first. Percent volume by volume would be more likely used in a case where you have a liquid dissolved in another liquid. So this is often used for like an, for instance, something like vinegar. Vinegar is acetic acid, okay, but it's just very diluted. So it's like liquid, like an acetic acid solution that's diluted with water. So it's a liquid in a liquid. Okay, so if you have a bottle of vinegar at home, go look on your vinegar bottle and you'll see that there's a percentage on your vinegar, and it will tell you what percentage of the solution, volume by volume, is made of acetic acid. So that's something you could do at home that would relate this concept. Okay, so here it says the volume of a solute dissolved as a percent of the volume of the solution, used when, this should say, one liquid is dissolved in another. So for example, 300 milliliters of acetic acid is dissolved in 1 liter of water. Okay, so let's see what that works out to be percentage-wise, and then you could compare it to the percentage that you'll find on your vinegar at home. And there's a variety of different, like you can buy just regular household vinegar, you can buy pickling vinegar, which would be a little bit stronger, you can buy cleaning vinegar, may have a similar concentration to pickling, I can't remember. Okay, so what we're going to do is we're going to first of all get our entire volume. Okay, so if we're adding 300 milliliters to 1 liter, the solution in total is going to have a total volume of 300 milliliters plus, well, 1 liter is 1,000 milliliters. So in total, we have a volume of 1,300 milliliters. Okay. Then what we do with that is we want to compare the volume of the acetic acid to the total volume and multiply by 100. Okay, so so you could do this in, as long as you stay consistent with your unit, it really doesn't matter what unit you use. So I could do 300 divided by 1,000, or I could do 0.3 liters divided by 1. Either way, I will work out the same. So I'm going to take my 300 milliliters of the acetic acid, and I want to know what percentage is that of the total volume. So here's my total volume. To make it a percentage, I multiply by 100. So when I divide and then multiply by 100, I get a 23.08% acetic acid by volume. Now I believe household vinegar is 5%. I'm just going to go double check. Yes, so if you do, I just checked my bottle of vinegar. It is in fact 5%, and it says it right on the front of the bottle, 5% acetic acid by volume. So this would be a very much stronger concentration. You wouldn't want to be sprinkling this on your fries or anything, because this is a lot more concentrated. But that just gives you a kind of common application of this concentration. Okay, we'll flip to the next one. Now these ones, I would think you've heard parts per million and parts per billion at some point in your life. This is sometimes used to measure, for instance, like how much of a pollutant is in an environment, or in so like in the air or in a water body. Parts per million or parts per billion. Sometimes another application would be a swimming pool or a hot tub. If you have those at home, you could measure, you know, the concentration of your chlorine or bromine or whatever it is you're using to keep your hot tub or pool like clean and sanitized. So these are used in like a larger, usually in really large volumes. Okay, so this unit, we'll start with parts per million. This unit describes the mass of a solute dissolved in a mass of a solution. 1 part per million means 1 gram of solute per 1 million grams of the solution. Okay, so it's a part per million. So you could use grams, or you could use really any unit of measure. It just means one of those units for every 1 million. Okay, so in this case, we're going to talk about grams, but really it's just 1 part per every million parts. So 1 part per million is a very, very small concentration, right? If you have 1 million pieces of something, only one of those pieces would include the solute, whatever that happens to be. So let's stick with our sodium chloride and see what this would work out to in parts per million. So if we have 2.2 milligrams of sodium chloride dissolved in 250 grams of water, how can we figure out how many parts per million that is? So first of all, we want to make sure that we're in the same unit here. We're in milligrams and grams, so we can't compare those two amounts until they're in the same unit. So let's convert milligrams to grams first. Okay, so 2.2 milligrams. Okay, now milli means 1,000th. So in 1 gram, there are 1,000 milligrams. You can always think about millimeters and meters. You would probably know that there's 1,000 millimeters in a meter. Okay, so if I divide by 1,000, that would give me 0.0022 grams. Okay, so very small amount. So now we're going to compare the amount of grams of solute compared to the amount of grams of water, and we're going to just make an equivalent fraction over 1 million. So I'll show you what I mean. So we're going to go 0.0022 grams over 250 grams is equivalent to, let's make this 1 million, because we want to know how many parts in a million parts, and what would that have to be equal to. So to solve for x, what you do is you cross multiply, okay, and then you solve for x. So when you cross multiply, you're going to multiply 0.0022 by a million. Okay, so I'm just going to have to put this over here. So we're going to move our decimal then 6 spots. 1, 2, 3, 4, 0.56 equals 250x. And then we'll divide by 250 on both sides. And we'll get that x is equal to 8.8. So 8.8 parts per million. Okay, so if we have 1,000,000 parts, about 9 of those parts would be the sodium chloride and the rest of the parts would be water. Okay, so that's one way. The parts per billion is really the exact same concept. It's just that we're doing how many parts out of 1,000,000,000 parts. Okay, so we would use the parts per billion in a larger, it would make more sense to use it in a larger volume. Okay, a little bit smaller volume, we'd use parts per million. So this unit is similar to parts per million, but represents 1 gram of solute per 1 billion, so 9 zeros, of solution. So let's do the exact same, or not, it's not the exact same because now we're dealing with 25 kilograms of water versus 250 grams. So a much, much larger volume, therefore parts per billion is a better fit. So again, we want to, in order to compare these volumes, we have to make sure they're in the same unit. So let's just go everything to grams. So 2.2 milligrams, we're going to convert it to grams. So in 1 gram, there's 1,000 milligrams. So that's going to give me the same 0.0022 grams. Now let's also put the 25 kilograms into grams, and then we're comparing apples to apples. Whoops. Okay, so here in 1 kilogram, there's 1,000 grams. So 25 times 1,000 is 25,000. Okay, so now we're going to set up our equivalent fractions. So we have 0.0022 grams per 25,000 grams. What is the equivalent fraction if we're dealing with 1 billion grams or parts? Right, so you're going to crisscross. So this time we'll move over 9 zeros. So this would be 2, 3, 4, so 5 there, and 25,000 times x, it's just 25,000x, and then we'll divide by 25,000 on both sides. So x is equal to 88 parts per billion. Okay, so significantly more concentrated, right? Almost like a 10-fold, well, exactly a 10-fold actually, increase in concentration. So 88 out of 1 billion parts are the solute, and yeah, so that is just kind of reviews some other ways to measure concentration. So in chemistry, we stick to moles per liter, but these are good to have an understanding of because you will come across these types of measurements in your everyday life. So there is no assignment that goes along with this. So if you have other stuff from the course to catch up on, you could work on that today. And next class, we will review our last few topics of the unit.